thing that we need to keep in mind that needs to happen for quantum computing to become successful: error correction and fault tolerance. Yesterday, we discussed a lot about this near-term algorithms, mainly the hybrid quantum classical algorithms. And I also told you that these algorithms are not necessarily um, these algorithms are not necessarily the best algorithms to reach utility or advantage because of many issues, but they are pretty good for near-term cases. And we are also going for this quantum-centric supercomputing, new type of algorithms and everything. However, none of those reduces the importance of error correction and fault tolerance. There is noise in the system today, and to deal with that noise, we need to have error correction. We need to have fault tolerance, and we will talk about how these two are different and what they mean. So simple thing, error correction is that when an error occurs, I should be able to identify that an error has occurred. I should be able to identify which type of error has occurred and where, like on which qubit, which type of error has occurred, and I should be able to undo it. So if we think classically, what do we do? I mean, this is a very simple example. Of course, this is not uh, the most one of not some of the most sophisticated codes, but let's start with the simplest classical repetition code. Simple thing is that if I am sending 0, or let's say that I am sending some bit b, which can be either 0 or 1, and this is the sender, this is the receiver. In between there is a noisy channel, and this receiver has received 0. Now if the receiver receives 0, it doesn't tell him whether the sender has actually sent 0 or the sender sent 1 and it got flipped here. Either one of these two is possible, right? So that makes it a difficult situation in this point. And therefore, what can be done is, what is the natural thing that people do when we say, I'm talking to you and you didn't catch a word? What is the natural thing that you would say? You would just ask me to repeat. Can you repeat once more? So here, let's say that instead of sending the bit 1, the sender sends the bit twice. Same bit, whatever the sender was sending, sends it twice, and we still have the noisy channel. Now, a few things can happen. At this point, the receiver not sure if B is 0 or 1. Now, let's say the receiver received 0, 0. Two things could have happened here. Either both of the bits were 0 or both the bits were flipped from 1 to 0, right? What is a bit more, but if it is 0, 0, something we can think of is that something called a majority voting, and we can say that the probability of error is less than half. Therefore, the probability that both the bits flipped is very low. Therefore, we don't expect that both of the bits have flipped and I am receiving 0, 0, but actually it was 1, 1 what was sent. Similarly, if I receive 1, 1, I would again make the same argument that it seems that the possibility that both the bits got flipped is lower. Therefore, I expect that the actual bit that the sender was sending was 1. None of the bits were flipped. So this comes from majority voting. This idea is called majority voting, that whatever the majority is saying, you accept that. You accept that the majority cannot be wrong at the same time. But if I receive 0, 1 or 1, 0, what happens now? Now I am sure that an error has occurred. So let's say that I am receiving 0, 1. The question here is, was the bit actually 0, the second bit got flipped to 1, or the bit was actually 1, the second bit got flipped I mean, the first bit got flipped to 0. Either of this is possible, and there is no way I can identify between these two. So here the point is that error has been detected, but error has not been, it is not possible. I can detect the presence of error, but what was the requirement for error correction? I need to detect error has happened. I am able to do that here, but at the same time, I need to know where the error has happened. Only then I can go and correct the error. But this second part, where the error has happened, this is not very clear to me. So this is detection. This is detection. But I cannot correct it. So what we do here, of course, I mean, this is very famous, is we can send it 3 times. And now, if I get something like, say, 011, example, if I get something like 011, I can again do majority voting and say that, okay, it was actually the first bit which has been flipped, because the other 2 bits are saying 0. So I will say that this bit was flipped. This bit was flipped. Therefore, my correct outcome is 111. This is the correct result. That means the sender was sending 1. This is how we can do correction here. The natural question here is that, can it not happen that actually the sender was sending 000, but both of the bits here got flipped to 1? So when I'm say receiving 011, then actually it was the sender was sending 000, but 2 of the bits got flipped. Can it not happen? Yes, it can happen. But here I cannot really correct a scenario like this. So what it means is that if we see, there is something called a distance of the code. Distance of code, D. In general, here the example that we are seeing is a D equal to 3 repetition code. And if I have a D equal to 3 repetition code, I will be able to correct T equal to floor of D minus 1 by 2 errors can be corrected. So here, as you can see, that I can correct only one error, and we realized immediately that if the actual bit was 000 and 2 errors have occurred, I cannot correct it using this, right? But I can detect, right? I can detect that error has happened. I cannot correct it. So I can detect up to D minus 1 errors can be detected, but only D minus 1 by 2 can be corrected. So what if I want to correct more than one error? I can go for a D equal to 5 repetition code. So if I go for a D equal to 5 repetition code, then just from this calculation, I will be able to correct T minus 1 by 2. That means 2 errors can be corrected. And we can very easily see that if I say, if my received bit is received bit is, say, 01100, I can still do a majority voting here and say that, okay, 3 of the bits are 0. That means I am assuming that majority of them are correct. So the same argument goes here. If 3 of the bits are 0, then I am assuming majority of them are correct. That means these two are wrong. These bits were flipped. And then if once I know which bits were flipped, I can just go ahead and correct it. So my corrected thing is, which is 0, right? So this is the very simple repetition code that we can do on a classical computer. And if we look into some of the terminologies, we have already seen what is the distance of a code. Distance of a code kind of tells us how many errors can be corrected. And there is something called encoding. So when I am taking, say, B, and I am creating BBB, this process is called encoding. I am applying a few more qubits. I am putting in some redundancy to actually ensure that I can correct errors. So this is called encoding. This is called the logical bit. This is called logical bit. In other sense, what I can think of this is that we can always consider BBB as a single bit. So as if I am just zooming out, and instead of looking at three of them, I am looking at three of them individually. I am looking at all three of them collectively and saying it is a single bit. So to differentiate it between the actual bit B and this kind of zoomed out case where three physical bits corresponds to a single bit, I call this a logical bit. So a logical bit is error corrected, a physical bit is not, right? So we will use the same terminologies here. There is one more terminology that we can just use here. See, when I was doing this kind of majority voting, this process, not necessarily doing majority voting is not the only way of correcting errors. This is a very simple repetition code, so majority voting works, but we have way more sophisticated codes, and there are way more sophisticated ways to detect the presence of error. And so see, whenever we say of correction, correction always is followed as detection with some correcting steps. So the important step here is actually to identify that an error has occurred, where an error has occurred. So this detection is important, and this thing, so there are three steps. If we see, detect that error has occurred, next is identify the erroneous bits. Next is identify erroneous bits. And finally, correct the erroneous bits. These two together is called decoding. This is encoding and this is decoding. When we decode, we know where error has occurred, and then we can just go, how do we correct the error? It's very simple. So when I say that I need to go from 0 1 1 0 0, I'll just apply two NOT gates here, right? That's how we can correct the states. So this is essentially what an entire error correction module looks like. That we start with a bit, we have a bit B, we undergo encoding, which gives us, say, BBB. This is the logical bit. Next, we have a noisy channel. This is our noisy channel. Finally, we go and we do something called decoding, which tells us the position of error. It tells me position of error. And next, I just go and correct. So this is correction. Correction is essentially flipping bits back, and I can hope to get B back from here. So this is my entire framework of error correction. Now the natural question is that can I take this to quantum directly? What is stopping me, or whether anything at all is stopping me from taking this to quantum? So let's look into our steps a bit carefully. So when I said that you need to start from a bit and encoding, we can do a sort of repetition of this. So issues with quantum. Issues with quantum. The first thing is repetition is not allowed. And I hope you can identify why repetition is not allowed. Any thoughts why repetition is not allowed? So this is basically no cloning theory. I cannot just take a quantum state. So see, when I am talking of quantum, my B is no longer necessarily 0 or 1. A B can be something like alpha 0 plus beta 1. It can be a superposition state. And therefore, repetition is not allowed, is the very famous no cloning theorem. I cannot just take an arbitrary qubit and keep repeating that like the way we did repetition. Second, how many types of errors are possible? Here, classically, it was only a bit flip error. So whenever I was talking of noise, noise looks something like this. If we think, noise looks something like this, that I have a state 0 with probability 1 minus p, it remains 0, and with probability p, it becomes 1. Similarly, I have a state 1 with probability 1 minus p, it remains 1, and with probability p, it becomes 0. This is called the binary symmetric channel. This is called the binary symmetric channel. Now, what are the different kind of errors that can, this is the only kind of error that can occur classically. Yes, you can say that, okay, maybe I have a channel where the p's are different. It's not a binary symmetric channel, it's an asymmetric channel. So all those things are fine, that 0 becomes 1 with probability p0 and 1 becomes 0 with probability p1, where p1 and p0 are not the same. Yes, these are all fine, but essentially it's just bit flip. Whether the probability is the same or different, that's a different issue, but it's a bit flip. That's all that can happen classically. Now, quantum mechanically, error is an operator. It's an unwanted operator, but I should be able to write error as an operator. Error is an operator. So when error is an operator, what are the possible errors? Infinitely many. Infinitely. Why so? Why infinitely many? Infinitely many. Because when error is an operator, it's an unitary matrix. Unitary matrix essentially means a rotation. How many possible angles of rotation are there? Infinitely many. So there are infinitely many possible errors that can occur on the quantum state. That is not acceptable. Third, when I say decoding, right? When I say decoding, what did we do in decoding? If we just become very crude and try to point out every step to, I mean, more clearly than required, here we have this 0 1 1. Okay, and I said that okay, we kind of assumed that majority is correct, so 1 is correct, 0 has been flipped. What we didn't tell, and this is something we don't tell when it comes to classical, that is so obvious, that we have checked the bits, whether the bits are 0 or 1, that we have observed, that we have checked. And immediately you understand in quantum, observation collapses the state. Which means if I just go and say that, okay, I have been able to do, let's say that somehow I have been able to find a way to encode, somehow I have been able to tackle with this infinitely many unitary operators which can be errors. But even then, when I just go for decoding, which means when I just observe the state will collapse, all the information is lost in the system. So naturally, this was the reason why there was a long period for which people thought that error correction is not possible in quantum, which makes quantum useless, practically speaking, which makes quantum useless. So one of the major things that Shor did was actually showing that error correction is possible in quantum. And if we stick to a scenario, let's start with a simple scenario. We'll start with a simple scenario where I am assuming only bit flip is possible. So I am making an assumption only bit flip is possible. Of course, this is not a complete scenario. I am making a relaxation on this point too. But let's see that if I make this assumption, can I still somehow do something about point 1 and point 3? So what I cannot do is, if I take, say, my psi is alpha 0 plus beta 1, I cannot do a psi logical, which will be alpha 0 plus beta 1 three times. This is not possible because of no cloning theorem. I see. Okay, there is a question that yes. So error is an operator, right? So when I talk of that an error has occurred, what does it mean? When I have a quantum state B, it evolves into something like E of B, where E is an error. So it's an operator. It's an operator that I didn't want to apply. It happened because of interaction with the environment or something. It happened. That means if it is an operator, that means it needs to be unitary. Of course, I mean, um, you can think of errors more as a quantum channel, but let's not go there. Let's stick to this point that it is unitary. Unitary implies rotation. How many possible angles of rotation? Infinitely many possible angle of rotation. It's the rotation angle will be a floating point number, a real number. Right? So this is not possible. Then how do we do it? So okay, can you elaborate a bit more? If error is an operator, it can be easily controlled. How? Because error is an unwanted operator. I mean, say let's say that you want to apply something like 0 followed by a Hadamard gate followed by a S gate. Say this is my actual circuit. Let's make it green. Sorry. Let's make it green. This is my actual circuit. Let's say intended circuit. So I start a single qubit circuit. I am supposed to apply Hadamard and let's say an S gate, and finally I measure. This is the circuit. No, so you are making a mistake. Gates are used to make an operator, true, but you are not applying this. If you write a code in Qiskit, this is a circuit that you are writing. You are explicitly saying apply a Hadamard gate, apply an S gate. This is the circuit that you are writing, but actual circuit that gets implemented because of interaction with the environment is maybe something like this. and X gate falls between these two, and you have no idea that this has happened because you wrote this one. This is the one that you have wrote. You have asked this to be run on a quantum computer, but when it goes to a quantum computer, when these pulses are operated on those, it interacts with the environment, and X pulse actually occurs, which you didn't ask for. So now you will get some incorrect answer, incorrect solution, but you don't know that an X gate has occurred here. So yes, it is true, gates are used to make an operator. So even here, I am mathematically putting a symbol as if an gate is applied. That is the mathematical way of representing this, that it's an operator, but it's an unwanted operator that you didn't put in. It can, it can get, it can just be inserted anywhere in the circuit without your knowledge. You have no idea that one of these operators have been inserted in the circuit. Now you have to correct for it. So that's how we mathematically want to think of this. So the natural thing is that psi going to this alpha 0 plus beta 1, yes, it is side effect of decoherence. It is side effect of decoherence. The way decoherence work, we can always consider it like a gate acting on a quantum circuit, but I am not aware of what gate and where in the quantum circuit. This is what I am not aware of. Okay, great. So what we can do is, I can take alpha 0 plus beta 1 and I can convert it into psi logical alpha 0 0 0 plus beta 1 1 1. This is possible, right? This is not violating no cloning theorem, because alpha 0 0 0 plus beta 1 1 1 is not equal to alpha 0 plus beta 1 tensor 3, because when I take tensors, there will be these other terms 0 1 1 0 1 0, all of these terms will be there. But here I am creating a circuit. How do I create this circuit? If you just take the state psi here and you start with two more qubits which are both in the state 0, psi is alpha 0 plus beta 1. I apply a C naught from here to here, and I apply a second C naught from here to here. What happens? Alpha 0 plus beta 1, and the next two qubits were 0 0, which is basically alpha 0 0 0 plus beta 1 0 0. Now I apply the first C naught, which goes from qubit 1 to qubit 2. So in the first case, qubit 1 is 0, so nothing happens on qubit 2, alpha 0 0 0, it remains. In the second case, qubit 1 is 1, that means qubit 2 will be flipped. So it will become 1 1 0. I have again another CNOT gate from qubit 1 to qubit 3. So here also qubit 1 is 0, so nothing happens. Here qubit 1 is 1, therefore qubit 3 will be flipped. So 1 1 1. That means what we just showed, it is possible to create this. It is a very simple circuit. It is possible to create this. So once I create this, what I get here, these three qubits together, I will call as my psi logical. This is my, all the three qubits taken together is my psi logical. Now it is going through a quantum channel, which, as we discussed just now, which is the error operator. It is an operator. I don't know what this channel is doing to my system. So this is essentially an operator, true, mathematically speaking, but it can even be identity, which means nothing happened. It can be any unitary here, which I am unaware of. Now the point is that I cannot measure the qubits at this point. If I measure the qubits at this point, then my system will collapse, right? The state is alpha 0 0 plus beta 1 1. Say if I measure qubit 1, then either it will collapse, everything will collapse to 0 0 0, or everything will collapse to 1 1 1 with certain probability. That is depends on alpha and beta. And if that happens, my information, that was my qubit alpha 0 plus beta 1, this information is lost. So I cannot do that. Now, so the question is that how do I decode the system? To decode the system, we need to understand one thing. We need to understand that I don't really need to know the entire state. Yes, alpha 000 beta 111, it is entangled. It is essentially like a GHZ state, not exactly a GHZ state. It is like a GHZ state, so it is entangled. Now, what we can think of is, let's say an X error has occurred on qubit 1. Okay, let's just assume that an X error has occurred on qubit 1. How do we represent that? I will represent X on first qubit and identity on second and third qubit. This is how we represent that X error has occurred. And this operator is acting on alpha 000 plus beta 111. What we get then, the first qubit will be flipped. So it will become alpha 100 plus beta 011, right? All I need to know, if you think at this point, all I need to know, these two qubits are in the same parity. Whether they are 0 or whether they are 1, these two have the same parity. And at the same time, these two qubits, first and second has the same parity, second and third has the same parity, right? I mean, you could also say that first and third has the same parity. That's fine. That's totally fine. So let me first tell you what is done, and then we will mathematically see that it actually works. I will take two more qubits. These qubits are called ancilla qubits. These are my ancilla qubits. Ancilla qubits always means that they are some extra qubits which are not part of my actual workload. My actual work is going on in these three qubits, right? Everything that I do will just happen in these three qubits. But ancilla qubits are something that I will use to extract some information of this system without actually disturbing the system. So what I will do is I will create a C naught, then another pair of C naught. And finally, I will measure these qubits, these ancilla qubits. What happens if I do that? Let's see. So here, this is my erroneous qubit. This is my erroneous state. An example, this is my erroneous state. Now I have my ancilla qubits, which are both in the state 0. So if I just put in 10000 plus beta 01100. Now I apply my first C naught. Remember, first C naught is between first qubit and the first qubit of the ancilla qubits. So it is between 1 and 0. This is 1, so this qubit will change. 100, this is 10, plus beta, but this is 0, so nothing actually happens. So it is 01100. I have a second qubit, Cx. This second qubit is between this, the second C naught is between second qubit and the first qubit here. So here my second qubit is 0, so nothing happens to the first qubit. And here my second qubit is 1, so my first qubit is flipped. I have two more C naughts, again from the second qubit to the last qubit, and then from the third qubit to the last qubit. So I have from my second qubit to the last qubit. Second qubit is 0, so nothing happens to the last qubit. Beta. Second qubit is 1, that means this last qubit is flipped. Now I have between this last qubit here and last qubit here. So 1 0 0. This is the last qubit, which is 0. So nothing happens. Similarly, here the last qubit is 1. That means this will be flipped. Now what I can just do is I can simply say this is alpha 0 0 plus beta 0 1 1, and 1 0 is common. This is the ancilla qubit. Ancilla qubit started with 0 0. It has changed to 1 0. This process where, see, I haven't learned anything about the qubit, but this is telling me ancilla qubit 1 0 is telling me there is X error on qubit 1. This, so once I know that there is X error on qubit 1, I can just go and apply an X gate on qubit 1. So there was an unwanted X gate. I have, via this calculation, I have realized that that unwanted X gate has happened on qubit 1. So I will now forcefully apply another X gate on qubit 1, and those two X gate will cancel each other out. So that's my correction part. This part where I am getting this parity information, this is called syndrome extraction. This is called syndrome extraction. It is getting my syndrome, and whatever I get here, the outcomes here, this is called the syndrome. So my 1 0, this 1 0 is my syndrome. This is my syndrome. And it will take a bit long time for us if you just want to explicitly calculate. So instead of explicitly calculating, let me just write down this table, and I would encourage you to go and try it out. The same calculation that we did is that if I have this error, and if I look into the syndrome, and finally this is my correction. Correction is what I need to apply. So if my error is, if say no error, then I start with 0 0 as my ancilla qubits. I will end with 0 0. This is my syndrome. Correction is identity. That means no correction. Applying an identity gate means no correction. Next, X error can happen on first qubit. So when I write X1, I mean X error happening on the first qubit. And here we explicitly calculated and we saw that the syndrome becomes 1 0. So the correction is also X1. It's, I mean, the correction and the error will be the same for our case. Second, what can happen? Happening on qubit 2 or qubit 3. Right? Because although this is the qubit that I am interested in, this is my original, this is called the data qubit. This is my original data qubit. But the error, I am encoding it and I am sending all the 3 qubits through the error channel. So there is no guarantee that error will only act on the first qubit. And if error acts on the second and third qubit, if I don't correct it, if I just say that, oh, I am not interested in the second or third qubit, if I don't correct it, then my logical state becomes incorrect. The logical state that I am creating, this shy logical, becomes incorrect. And this shy logical is where I will do my computation on. And the entire computation becomes incorrect. So you can easily check that X2 gives a syndrome of 1 1, X3 gives a syndrome of 0 1. Right? So I'll just encourage you really to go and try this other two out that we didn't explicitly calculate. It will be just the same steps. Just apply the error and then keep applying these C naughts one after another, and you will be able to take out the syndrome bits and you will get the proper syndrome from here. This step is the decoding. So why I am explicitly mentioning this is actually important because decoding is classical. See, when I am saying that this is happening, this calculation that we did here is applying the C naught gates. This is the syndrome extraction, and the outcome of the bits is called the syndrome. But looking into the syndrome 1 0, what will you do? Let's be very explicit. What will you do? You will go and refer to this table. Oh, 1 0 means there has been an X error on the first qubit. This inference 1 0 means there has been an X error on the first qubit. This inference is the decoding, and decoding is classical because you are just referring here, you are just referring to a table. There are other more sophisticated codes and more sophisticated classic decoding techniques, but here I am just referring to a table. But any code, any decoding technique that we can think of, however sophisticated it be, the decoding is always classical. And again, when I am doing the correction, it will be a quantum state. So I look into the syndrome, and then I will, what will I do? I will look into the syndrome and I will make a controlled operation. On the outcome of these two, I will apply a correction here. So this will be a correction. And this correction is controlled by this syndrome bit. This is an entirety of what error correction looks like, right? One more question here. Let's say that you have this state alpha 0 plus beta 1. I want to actually apply an X gate on that, not an error. So what if I want to, how do I do computation on this? How to compute? The question next is how to compute. Say I want to apply X gate on qubit on psi. Say this is actually my circuit, that you create the state psi and then you apply an X gate. This is my intended circuit, not my error circuit. But the moment you take psi from psi, the moment you get it to psi logical, which is a 3-qubit state, and you create this psi logical, now if you apply X on the first gate, you saw what will happen. We just did this, right? When X was applied on the first qubit, it went through this error correction scenario and it was detected as an error and it was corrected. So if I do this, then this will be treated as an error. But so what we need to do here, we cannot just do this. Since we are encoding our qubit, we need to encode our gates as well. So here what I should be doing is my psi logical X, X, X. This should be my, these three X together we can consider as my logical X. So now I can think of this as if my psi logical is a qubit and X logical is acting on it. This is how the computation will go. This is the logical gate. And this is the logical qubit. So just like we had multiple qubits coming together to implement a logical qubit, we will have multiple gates coming together to implement a logical gate. Now, for certain gates, what I showed here, it is actually easy to check because what do you want? You want, when you apply an X gate, your alpha 0 plus beta 1 after applying an X gate should become alpha 1 plus beta 0. Now, currently you have alpha 0 0 0 plus beta 111. This is how we have encoded it. That means I can think of this as if this is alpha 0 logical plus beta 1 logical, where my 0 logical is 000 and 1 logical is 111. Now, if I apply this X logical on this, which is one X gate on each of the physical qubit, it will become alpha 111 plus beta 000, which is equal to alpha 1 logical plus beta 0 logical. Done. This is what we wanted. Alpha 0 plus beta 1 should go to alpha 1 plus beta 0. So here alpha 0 logical plus beta 1 logical goes to alpha 1 logical plus beta 0 logical. So this is how we actually compute after encoding. And in fact, in order to maintain a proper error corrected state, this is what we have to do. We have to first encode the qubit, and throughout our computation, we cannot remove this encoding. We encode only once in the beginning. Every computation that will happen on this is like this logical computation, and we will multiple times at some interval I will keep doing this syndrome extraction, and I will check whether an error has occurred, and I will go and correct it. So if we want to think of the entire workflow now, we will say that you take the state psi, you encode it, this will give you psi logical. Now apply logical gate. You can decide how many logical gate. It need not be a single logical gate. Maybe you apply multiple logical gates. And then you have to do syndrome extraction and correction. And this will be repeated. This will be repeated throughout your computation. There will be multiple syndrome extractions and there will be multiple logical operations. How far do you put your syndrome extraction? That will depend on a lot of things. One of my PhD works was on actually something called error tracing, which kind of used the error information. Not my PhD work, this was my master's work. Yeah, this was another friend's PhD work. This was my master's work, where we kind of showed that you can calculate the probability of error, and you can take a decision of how the errors accumulate, and therefore how far you have to do syndrome extraction to maintain a certain threshold of noise and something, right? But we won't go into that here. One important point here is you may want to apply many gates on your quantum circuit, right? You need not only apply an X gate, there can be many unitary operators that you would want to. Okay, okay. So you may want to apply many of these operators. Can I always say that if I have an U, the logical version of that U logical is basically U, U, U? Is this guaranteed? And the answer is no, this is not guaranteed. There are certain gates for which to create the logical gate, you can just apply the same physical gate on each of the physical qubits. If that happens, then such a gate is called, if this happens, if this happens, then this gate is called a transversal gate. If this doesn't happen, else it is called a non-transversal gate. Whether a gate is transversal or not depends on the error correcting code. So it is possible that I have designed my own error correcting code, and a set of gates are transversal there, a set of gates are non-transversal there. You design your error correcting code, this set can change. But for majority of the codes that we use today, almost for every code that we use today, if we look into the Clifford plus T library, we know that every unitary can be decomposed using this Clifford plus T gates. That means if I have any unitary U, you can always represent the unitary using some cascading form of gates coming from this Clifford plus T library. This T gate is usually non-transversal. Non-transversal gates often require, we won't go into that, I mean we will, otherwise we will digress a lot, we won't go into that. But non-transversal gates often require a huge amount of resource to implement the gate. You can immediately understand that here, instead of a single gate, I am having to apply 3 gates. If you make a distance 5 repetition code, you will have to apply 5 gates. The resource is anyway increasing. But if it is non-transversal, first, it is often a research on its own merit, that if you are given a code, and if a gate is non-transversal there, how do you implement the logical version of that gate for this code? There is no straight cut answer to this. It is often a research problem in its own merit. And usually when a gate is non-transversal, it requires a lot more extra gates to implement it, making it very difficult. So you will see there is a lot of these things like magic state creation and everything, and these are some of the more efficient methods to implement T gates on the quantum error correcting codes that we use today. Having said that, there are research on error correcting codes where T gate is transversal, then the Clifford part becomes non-transversal. And that is actually way more costly, because Clifford is not a single gate, it is a lot more gates which are in Clifford. So you won't want an entire set of multiple gates to become non-transversal just to make a single gate transversal. So all of these researches are possible, strictly speaking, but practically speaking, we always resort to this kind of gates where Clifford plus T gate, Clifford is transversal, T is non-transversal. Okay. Yeah. Any questions up to this? So what we have seen here is we had 3 problems to apply error correction. We see how we can avoid this first problem, that repetition is not allowed. We have been able to bypass it and create an error correcting code. The third was that observation collapses the state, and we have been able to apply this ancilla qubits and follow it up with this syndrome extraction state to syndrome extraction circuit to go and get the syndrome and therefore correct. It only gives me the parity of the system. It doesn't tell me anything about the system. Therefore, the system does not collapse. What we haven't looked into yet is error is an operator. Therefore, there are infinitely many possible errors. And we have just taken an example that let's assume that only bit flip error is possible. And we have designed an entire error correcting code here. We have understood each and every step of that. What is encoding, what is syndrome extraction, what is syndrome, what is decoding, everything we have understood here. And we have also understood that after we do this encoding in an error corrected scenario, how do we apply gates on encoded systems, and what are the challenges involved there? That is this transversal and non-transversal thing. So if there are any questions, we can take that. Otherwise, we will come and try to see how to get rid of that second point, that there are infinitely many errors. Okay. If not, let's come to the second part, that how do we take care of this fact that there are many errors in the system and it's not a single error, only not bit flip. So what is a possible error on the quantum state? We said that error is an operator. That means any unitary you can think of is a possible error. But the nice thing here is that we agree that any unitary is a possible error. So now let's make it blue. Let's look into how do we tackle with how to tackle So a nice thing here is that if I have a unitary U, let's consider a single qubit unitary for now, I can always write it as a linear combination of the Pauli gates. Right, with some coefficients ai, ax, ay, az, but I can always write it down like this. So if I think that this u is an error, so let's assume that u is my error. Any arbitrary unitary is my error, and my u is operating on my state psi logical, the encoded state psi logical, then I can write it like this. Now I will do syndrome extraction here. So I will add ancilla qubits. So okay, let's come back to blue because now we are going to correct things. So now I will add ancilla qubits and I'll add two of them. So just like before. So I am getting psi logical 00 plus ax x psi logical 00 plus ay y psi logical 00 plus az z psi logical 00. Right? Now when we apply the syndrome extraction circuit, what will happen? What will happen? Okay, just before coming here, let's come to this. Maybe it will make things a bit easier to deal with. Let's ask how to tackle Z error. How to tackle Z error. That is phase flip. Phase flip is something that cannot happen in classical, but it can very well happen in quantum. So let's assume that beyond X gate, I can also X error. I can also have this Z error, which is the phase flip error. So if we look into this, X error was essentially doing, it takes 0 to 1 and okay, and 1 to 0. This is how my bit flip works. How my phase flip works, it takes 0 to 0, it takes 1 to -1. So this is how my phase flip works, and apparently there is no relation between how these two work. So if I am able to correct bit flip, which I am able to do, that doesn't tell me how to correct my phase flips, right? However, if we just think of one thing, let's look into this state plus 1 over root 2 0 plus 1 minus, which is 1 over root 2 0, minus 1. Now, if I apply a Z gate here, what will happen? It will become 0, minus 1 because this is how Z operates. And if I apply a Z here, it will become 0, plus 1. So I can think of that it is essentially plus becomes minus, minus becomes plus. So my phase flip acts like a bit flip, but in the plus minus basis. This is a very important concept that my phase flip gate that I have here acts like a bit flip operator, but if I have a plus minus regime, not a 0 1 regime. And I know how to do that, right? Very simply, if I just take, instead of taking alpha 0 plus beta 1 to alpha 0 0 0 plus beta 1 1 1, if I just make it alpha plus 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 beta minus minus minus, how will I make it? I will do the same thing that I did here for encoding. I'll just apply Hadamard gates before, right? Just not by applying Z gates, not by applying Z gates. I'll just apply Hadamard gates. Hadamard gates changes 0 to plus and 1 to minus. I always start with 0, right? So I want to change, instead of encoding it as alpha 0 0 0 plus beta 1 1 1, I want to encode it as alpha plus 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 and beta minus minus minus. So what I will do is that I had this 3 qubit shy logical, which was previously my alpha 0 0 0. Previously this was alpha 0 0 0 plus beta 1 1 1. I mean, we know the circuit to do that. I'll just apply a Hadamard gate on each of them. I'm done. And now everything that we discussed here works. So everything that we discussed here will work now. Okay. Now let's come to this question. So let's, I would again encourage you to go and do this same calculation that we did here, every calculation that we did here for the Z gate. But I hope that it is quite obvious to you all at this point that whatever we did for this will immediately work for this. Just the syndromes will be plus plus, plus minus, like that, right? But everything else will be the same. Now let's try to answer this question. How do we tackle any error in the system? So what we realized is that when we have this any error, can I copy this? Can I copy this? Ah, nice. But I don't know how to paste it. Ah, okay. So this was my any error case, right? Now, if we think of that, I am going to add my add syndrome bits. So it becomes AI I shy logical 0 0 plus AX X shy logical 0 0. See that the system is actually entangled, right? 0 0 plus AZ Z shy logical 0 0. Now, the next step that I will do is my syndrome extraction. Note now that since the system is in an entangled state, a linear superposition of different states, it's entangled, but okay, it's fine. It's a linear superposition of each of these states. How does it, how do we work? See, when I'm doing this syndrome extraction, it is essentially a unitary operator, right? I am just applying 4 CNOT gates here. It is essentially a unitary operator. That is all. I can just consider all 4 of these CNOT gates bundled together as a single unitary operator. How does a unitary operator act on a superposition state? If I say have an u acting on alpha 0 plus beta 1, it is basically alpha u times 0 plus beta u times 1, right? This is how we apply on each of the states in the superposition individually. What happens when I do the syndrome measurement unitary? The ancilla qubits change into my syndrome. The ancilla qubits, which were started with 00, changes into the syndrome, which can be 00011011, whatever it is, but it will give me the error which is present in the system. This is what we have seen before. So if I do the same thing here, it will give me shy logical. I am just writing it like this: syndrome corresponding to the error identity. Plus, of course, there is no syndrome. If the error is identity, it is the syndrome is always, it starts with 00, it ends with 00. Syndrome corresponding to X. This 00 becomes syndrome corresponding to X. Plus AY, Y, shy logical. This becomes the syndrome corresponding to Y. AZ, Z, shy logical. This becomes the syndrome corresponding to Z. Now when I measure it, now when I measure syndrome bits, syndrome qubits, what happens? The state will collapse. The state will collapse to any one of them. Say the state collapses to X, just for an example. Say it collapses to X with probability this. So, no, let's not go for say. Let's see. With probability mod AI square, the state and the syndrome. The state becomes identity acting on psi L and the syndrome becomes SI. With probability mod AX square, this becomes X acting on psi L and the syndrome becomes SX. With probability mod AY square, this becomes Y acting on psi logical, this becomes SY, and with probability mod AZ square, this becomes Z acting on psi logical, this becomes SZ. But what is very, very super duper important here is that the state collapses. So I cannot have all of them at the same time. Any one of these four occurs. When I measure the system, any one of these four occurs. And if I get the syndrome corresponding to I error, that means no error. See, my state also doesn't have any error. If I get the syndrome corresponding to the X error, my state also has X error. It doesn't have any other kind of error. If I get the syndrome corresponding to Y error, my state has Y error. If I get the syndrome corresponding to Z error, my state has Z error. So once the system collapses, whatever my syndrome shows me, this is where entanglement plays the role. Whatever my syndrome shows me, that is the same error that is on the state. The state has also collapsed accordingly. So if I know how to correct these individually, then I know how to correct a unitary operator like this, a unitary error like this, right? Now, we have explicitly seen how to correct for this. We have not explicitly seen, but we kind of argued based on this correction of X error, how to correct this, how to correct Y error. Y is essentially X and Z. It is IXZ or IZX, something like that. I keep forgetting always. So if I correct for X error first and then for Z error, sequentially, one after another, I correct for Y error, right? That means, how do I do this? I will start with, say, shy. Let's say I correct X error. correct for X error. X error may have occurred, X error may not have occurred. That's okay. But I will always have a module which corrects for X error. Then I will have another module which corrects for Z error. And when I do both of them sequentially, they together correct for Y error. So if no error happens, these two modules don't do anything. If only X error happens, this module corrects the error, this module doesn't do anything. If only Z error happens, this module corrects the error, this module doesn't do anything. If Y error happens, the system treats it as a X and Z error sequentially one after another, and both of these blocks will correct their individual part, and we correct for Y error. So we can correct for any unitary using this method. The first error correcting code that was shown like this was the very famous 9 qubit code. What that is an important part that we need to, that will kind of complete the story. Here I said that if you want to correct for X error, you start with alpha 000 plus beta 111. If you want to correct for Z error, you make it alpha 1 plus 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 beta minus minus minus. What if you want to correct for both the errors? How will you encode? Because we discussed here that encoding is done only once in the beginning, and this syndrome extraction is repeated again and again. So this is the very famous short code. It's a 9 qubit code. What it does is its psi logical is alpha 0 logical plus beta 1 logical, where 0 logical is 9 qubit. It will be 1 over root 2. Yeah, 0 0 0 plus 1 1 1 tensor 3. Now you can immediately ask, oh, you just said tensor 3 is not allowed. What happened? You are just now doing tensor 3. No, look into this, that what it is just doing is it is still taking 0 0 0 plus 1 1 1, and it will take 0 0 0 minus 1 1 1. These are orthogonal states. So the moment this system takes an arbitrary quantum state alpha 0 plus beta 1 and maps it into two orthogonal logical states, I can clone the orthogonal states. That is something that no cloning theorem allows me. And one logical is 1 over 2 root 2. What this does is, as you can understand, this 0 0 0 plus 1 1 1, this we have seen is used to correct bit flip errors. And when I said it is tensor 3, this plus inside, this is the bit parity, this is the phase parity. This minus, it is the phase parity. This is also repeated 3 times. So this repetition of 3 times on the bits helped me correct the bit flip error. Repetition of these plus and minus signs 3 times helps me correct the phase flip errors. And when I do both of them sequentially, I can correct for any arbitrary unitary errors. So yeah, that's kind of going into short code. Let's once more just pause for a minute and see if there are questions. If not, we'll go for stabilizers. Sorry, I didn't get this question. Why short code? I mean, Peter Short discovered this code. That is why it's called short code. That tensor in the superscript kind of means that it is basically you cannot just correct both bit flip and phase flip using 3 qubits. So you need repetitions there also. This is what the code looks like. So essentially, this is a 9 qubit code. Reason to use shortcode. Once more, I don't get the question. I mean, why shouldn't we use the shortcode? I mean, shortcode is not used in the current quantum computers, but first is this is the first error correcting code, and we see how it very nicely and very intuitively shows us how to correct the errors and why these errors are getting corrected like this. This is the simplest to understand code essentially. So we always start with short code. And if you are asking something else, it will be better if you just elaborate it a bit. It is not 3 into 1 over square root 2. It is 1 over square root 2 for each of these three. Okay. Yeah, sorry. It is basically 1 over square root 2 for each of these blocks. So there are three blocks. There are 8 of them. So it will be 1 over square root 8, and that will be 2 root 2, like that. Okay, let's maybe move on then, if there are no immediate questions, um, to the stabilizer formulation, which is again very important. The way we kind of went ahead to understand this code was through circuits, by drawing circuits and all of those things. But of course, I mean, this is a bit clumsy. This is a bit clumsy. And one of the greatest inventions, I would say, in terms of error correcting codes is the stabilizers, which was done by Daniel Gottesman for his PhD thesis. He was a student of Preskill, if I remember well. And this stabilizer code is the idea. Stabilizer is not a code, it's a formalism. So the stabilizer formulation is his PhD thesis. He is right now a faculty in the Perimeter Institute. So let's go into the stabilizer formulation. The stabilizer formulation gives a very nice mathematical representation of an error correcting code. You don't need to remember this very clumsy zero logical, one logical. It is like this for this short code, but often these zero logical and one logical are very, very complicated for other codes. You don't have to remember the entire circuit, because as your system gets bigger and bigger, your circuit can get very, very complicated. So remembering all those things, or like storing all those things as my code, is quite complicated. So if we ask what is a stabilizer, then we can kind of answer it in a sense by saying that a stabilizer is essentially a set of operators created from the Pauli matrices XY set. Simple. So a stabilizer is a set of operators. Stabilizers are operators which are created from I, X, Y, Z for an n qubit system. For an n qubit system. We will see explicit examples of this, so don't worry. For an n qubit system, a stabilizer is built using identity XYZ. So each of the n qubits, there are, you can think of like there are n blanks, and you are allowed to put identity or X or Y or Z on each of them. The first requirement is that if SK is a stabilizer, then and Psi logical is the encoded state, then it should just give you Psi logical. That means my code word, this Psi logical, the encoded state, or you can call it the code word, it basically means that code word is a +1 eigenstate of every stabilizer. And I'm talking about non-trivial stabilizers. Like you can always take your stabilizer to be identity. All the bits I have identity operators, and then this always works. No, I'm talking of non-trivial operators, not identities. Secondly, for all error E that I am able to correct. So let's assume that I have a set of errors capital E that I can correct, as we discussed before, right? If I take a repetition 3 code, I will be able to correct up to a single error. So I'm, when I take this set E here, it's short code is a single qubit error correcting code. So that means I need to correct for a single error here. If there are two errors, I don't guarantee that I am going to correct that. So when I take this capital E is the set of all errors that I am claiming my code can correct. These are all single qubit errors. Then there exists some stabilizer, at least one. I am not claiming that there exists exactly one stabilizer. There exists at least one stabilizer, SJ, such that SJ acting on Psi logical will give you minus Psi logical. That means the error bit, or however I say, erroneous state is a -1 eigenstate of at least one stabilizer, right? Now the third thing is the stabilizers should commute with each other. So SK SJ should commute for all pairs K and J. For every pair K and J. What it means is it doesn't matter, because you see what we will immediately understand, and you kind of understand from here that instead of looking into the syndrome qubits now, mathematically I will say you look whether it's a +1 eigenstate or a -1 eigenstate. This is what we are going to look at. And here we said that you correct for X error, you correct for Z error. You could have said that no, I prefer Z error. I will correct for Z error first and X error next. That should not cause a problem. You should always have the ability to say that I will correct either for Z error first or I will correct for X error first. Whichever you choose to correct first, that should not hamper your error correcting mechanism. So this is what it means, that if you have two stabilizers, any two stabilizers should always commute with each other. This is what is meant here. So let's take the bit flip error as an example. Stabilizers. If you ask me how do you come up for stabilizers for an error correcting code, that is the research. I mean, if you know the stabilizer of an error correcting code, you know everything about the error correcting code. So there is no one shot formula to just tell that, okay, this is how you come up with an stabilizer for an error correcting code. But for these very well known codes, the stabilizers are known. So stabilizers for bit flip QECC. It was a 3-qubit code. The stabilizers are ZZI and IZZ. Okay. The stabilizers are ZZI and IZZ. You can ask why not ZIZ also? Because ZIZ is the product of these two. So ZIZ is not giving me any extra information. Therefore, we do not include ZIZ. So if I now take my state psi logical, which was alpha 000 plus beta 111, if I apply, this is the no error state, this is the correct code word, right? If I apply ZZI to psi logical, what I will see is, what will happen? Z acting on 0 gives 0, Z acting on 1 gives -1. So here both of them are 0, so nothing happens. And here both of them are 1, so there are 2 minus 1, and we essentially get a +1. So nothing happens. That means it's a +1 eigenstate. If I have IZZ, once more, these two are 0, so alpha 000, and these two are 1, 2 minus 1 coming together to give a +1, beta 111. So the first requirement is maintained, +1 eigenstate. Code word is the +1 eigenstate. Now let's think of x on the first qubit. This is what we saw as our previous example. So it was getting 100 plus beta 011. Now let's apply ZZI on x1 psi logical. What will happen? Z acting on this first qubit gives me minus, and this is 1, so minus, this is plus. That means minus alpha 100 plus ZZI. This 0 gives a +1, this 1 gives a -1, so it's not plus anymore, sorry. So it's minus beta 011. So that means it is minus of alpha 100 plus beta 011. So -1 eigenstate. And if I take IZZ, so see IZZ, both of them are 0, so nothing happens. Alpha, sorry, alpha 100 plus beta, both of them are 1, so 2 minus 1 makes a +1, 011. That is fine. So what the requirement was that there exists at least one stabilizer which will give me a -1 eigenvalue. So for this stabilizer gave me a -1 eigenvalue. This one didn't. That is totally fine. And if I now write down the same table that I did before, now see what is interesting here. This is something to actually keep in mind. This formulation or this calculation that I showed is way more tidy, way more easy and intuitive to understand. I won't say intuitive, maybe the circuit is more intuitive to understand, but it is more clumsy. Like you have to apply all these gates again and again and then do measurement, keep track of how it collapses. Everything you have to keep track of. The calculation is way more complicated and cumbersome here. The syndrome measurement here, the stabilizer measurement is extremely simple. You just apply an operator and you check whether it's +1 eigenvalue or -1 eigenvalue. But on a circuit, how do you just apply an operator and check whether the eigenvalue is +1 or -1? You cannot. Essentially, whatever we are doing here is, so what I did here, when x occurred on qubit 1, ZZI gave a -1 eigenvalue and IZZ gave a +1 eigenvalue. This corresponds to the same thing of saying that when I had this error on the first thing, the first qubit of my syndrome gave me 1, the second qubit 0. The syndrome should have been 0 if there were no error. And the second qubit here doesn't seem to indicate error, but the first qubit did. Same way, in the stabilizer, my first stabilizer gave me a -1, my second stabilizer gave me a +1, which is the correct syndrome for the correct eigenvalue for the code word. So essentially, what we did mathematically as a stabilizer, physically, if you want to implement, this is how the implementation goes. Whatever we learned till now, in before using the circuit, this is how the implementation goes. But the stabilizer formulation is mathematically simpler and easier to deal with, because now when I say a bit flip QECC, previously you had to remember the entire circuit and everything, but now if you just remember these two, you are done. These two gives you everything about the stabilizer of a bit flip QECC. So if I again come back to this, previously we had error and we were doing syndrome. Here now what I will do is I will do stabilizer 1, stabilizers, and the correction is actually the same as the error, so that is not very important at this point. So if I say in syndrome we had the qubit q0, the ancilla qubit q0 q1, or if you want I can just write it just for the sake, maybe, sorry, just for the sake I can maybe just to make sure that these are ancilla, I can write this as a0 and a1. And my stabilizers, let's call them S1 and S2. Now you will see the one-on-one correspondence. When there is identity, both of my syndromes were 0 and both of my stabilizers will give me +1 eigenstate. There is no correction. When I apply the gate X, I saw it was 1, 0, and here we saw that this was -1, this was +1, and your correction is X on the first qubit. When we had X on the second qubit, the bits were 1, 1, and you can just go and do the same calculation. It will be -1, -1. The correction is the same, and X3 it will be 0, 1, so it will be +1, -1, and the correction is X3. So you see, the stabilizer formulation is the same as what we studied using the syndrome extraction and everything, but it's simpler, it's easier to understand. So if we want to see how the short code is corrected, okay, there is one more thing. There is a fourth thing for stabilizers. If it is an n qubit system, there are n-1 stabilizers. Um, Strictly speaking, if you want to know, and if this is complicated, don't worry about this. Why this requirement is there is because if you have an n qubit system, it gives you a degree of freedom of 2 to the power n. It's kind of saying that 2 to the power n is the size of the Hilbert space for an n qubit system. When you have m stabilizers, out of those, you have kind of fixed that the code word should be such that for m of those, the code word should be a +1 eigenstate. So it kind of bounds to the power m degrees of freedom, is bounded. It is no longer free to use. So when you do a code word, and you have M stabilizers, the point is that for each of those M stabilizers, your code word should be a +1 eigenstate. So you cannot just take randomly anything that you want. That is not doable. So this M stabilizers kind of bounds the outcome of the degree of freedom of 2 to the power M. So you are left with 2 to the power n minus m degrees of freedom, which is equivalent to n minus m qubits. And this is what the logical qubit is about. So when we say that I, for an n qubit system, there should be n minus 1 stabilizers, that means out of n qubits, out of 3 qubits, if you see out of 3 qubits, I have 2 stabilizers. That means out of 2 to the power 3 degrees of freedom, 2 to the power 2 of them are kind of fixed. I am left with a 2 to the power 1 degree of freedom. So that is 2. 2 degrees of freedom corresponds to 1 qubit. So this is a logical qubit. Mathematically speaking, this is how logical qubits come. Again, if this is not very clear, don't worry about it at this point. The stabilizers for Shor code the stabilizers for Shor code, it's a 9 qubit code. So there will be 8 stabilizers because it's a 9 qubit code that is used to correct a single error correcting code. I'm sorry, a single error. So S1, S2, S3, S4, S5, S6, S7, S8. And let's take the 9 qubits Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, Q9. So the first one is ZZI. Remember how the short code is working. It is, if you look into zero logical, it is basically 000 plus 111 repeated 3 times. And we know that 000 plus 111 is actually used to correct bit flip error. This is what we have already seen, how to correct bit flip error. What are the stabilizers for bit flip error? ZZI, IZZ. So I will take each of this chunk, think of Q1, Q2, Q3 as a single chunk, Q4, Q5, Q6 as another single chunk. So I need to make sure that bit flip error is corrected on each of these chunks. So I have ZZI, IZZ. First chunk, bit flip error taken care of. Second chunk, bit flip error. So whatever I am keeping away here, these are all identities. Okay, just not writing it, it will become very cumbersome. IZZ. Third chunk, again, ZZI, IZZ. So using 6 stabilizers, I am able to account for bit flip error on each of the 3 chunks. Now you can kind of take a bird's eye view and you can say these two together is a chunk, and these two together is a chunk. You want to make sure that the plus here is repeated 3 times, the plus is accounted for. So ZZI was correcting for, this was accounting for the first qubit, second qubit. It was checking the parity of the first and second qubit. This is checking the parity of the second and third qubit. So if first and second are in the same parity, second and third are in the same parity, I know all 3 of them are in the same parity. Now what I need to say is if my first chunk and second chunk has the same parity of phase, this plus has the same parity of phase, and the second chunk and the third chunk has the same parity of phase, then all 3 of them has the same parity of phase. Now bit flip errors are corrected by Z. Z is used for to detect bit flip. Can any of you think why? If not, I'll just come back to this. Z is used to detect. Z does not mean bit flip. This is to detect. Z means phase flip. But Z operator is used to detect bit flip, and X operator is used to detect phase flip. So now I will consider this 1, 2, 3, 4, 5, 6, these as individual chunks, and now I want to apply an X, X, I, X, X, like this. How do I apply this X on 3 qubits? Remember, X is a transversal gate. We talked about that. X is a transversal gate. So X on 3 qubits essentially means X, X, X. X on 3 qubits essentially means X, X, X. And I is always transversal. So I on each qubit means I. Sorry, this should be S7. Sorry, this is S7. This S1, S2, S3, S4, S5, S6. This is S7. I, X, 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 X. Done. So these 8 stabilizers tell me everything about shortcode that I need to know. These, so the if you want to see the actual circuit of shortcode, that can become very complicated and very cumbersome. It is like really very cumbersome. But you see, this is very elegant and sophisticated. This is very elegant. So this is how any code is actually represented. The shortcode is represented like this. If you have already thought about why this is the case, because Z and X anti-commute. So if you have an X error, you want to put a Z operator so that they will anti-commute with each other, and they will give you the um, minus sign. If you want to think of how, think of it like this. I mean, this will be a very good exercise to do. If you have this, say, ZZI, and it is acting on xii, right? X on first qubit means I on second and third qubit, xxi psi l. Here we kind of physically calculated for every step, and we found out that this should be minus here. Now we can always say that when I have Z and X, I can just change the two operators, right? I can just change both of them, and I can just write that X comes before, Z comes after, but X and Z anti-commutes. So it is like this. See what happened? Z and X anti-commuted, Z and I commute with each other, I and I commute with each other. So only Z and X anti-commuted. That means I get a minus sign here. Now ZII is a stabilizer. ZII acting on the code word will give me +1 eigenstate. So this is essentially minus XII shy logical. So whatever we did here, all the calculations, if you just look into the commutation relationship, you can do the same calculation way more easily. And this is kind of the reason why Z is used to detect bit flip error. Sorry, what happened? Yeah. So this is why Z is used to detect bit flip error, and X is used to detect phase flip error. So this portion, these 6 are correcting for bit flip. These are accounting for bit flip error. These 2 are accounting for phase flip error. And together we have this 9 qubit error correcting code, which is the short code. Maybe I'll just stop here because we are almost at time. We are just 10 minutes early. I know we covered a lot, but I would say we didn't cover a lot also. So if you all are okay with it, I can just talk with Pilli sir or anyone to see if we can have one more extra session on quantum error correction, because this was important to go like this. I was assuming that at least some of you at least are seeing quantum error correction for the first time, but I would have really wanted to cover Steen code. Steen code gives me this, this short code seems to come out of the blue. In some sense, I just told you that if you think like this, then it works. This is how short code has been working. But Steam code has a very nice structure that comes from classical error correcting code, and that shows you how you can take any classical error correcting code and build your own quantum error correcting code. You don't have to think out of thin air and come up with something like a magic. This short code is kind of like coming out like a magic out of nowhere. But Steen gives a very much more well formulated method to see how we can take a error correcting code from classical and build it into a quantum state. The next code which is important is what we didn't get to talk a lot about is the CSS and non-CSS code. Um, this is a CSS code, but there are non-CSS codes, and this uses 9 qubits to correct one error. Classically, we saw we can use 3 bits to correct one error. Steam code uses 7 qubits to correct one error. There is another code by Laflem who showed that you can correct one error using 5 qubits, but it becomes a non-CSS code. So there are some pros and cons of that, and he showed that that is the minimal. You cannot go below 5 qubit if you want to perfectly correct a single error, and beyond that we should at least have some idea of what is surface code and how the decoding of surface code works. So yeah, let me know if you are interested. I can talk with Professor Pilli and see if we can have one more session on this. These are some parts that you should be knowing if you are doing a course on error correction. Okay, but I will stop here because if we just start any of these parts that I talked about, we will not be able to finish in time. We will go way beyond time. So let's not do that. Let's stop here and we can take questions. Is this common concept coming in measurement section of QVC? What is QVC? What's the significance of XXI and IXX? Okay, so when I was writing XXI, it kind of meant that I am assuming X is acting on 3 qubits. Of course, X cannot act on 3 qubits. So here what happens is all three of this is my X. So just like I had ZZI, I essentially have XXI, which is just correcting for my phase flip error, but it is working on a chunk in total, and each x corresponds to 3 physical x. That's how we saw the logical operators work, right? uh, okay, coming to this, no, this has nothing to do with quantum variational circuits. Although, I mean, I know yesterday we talked about plus one, minus one eigenvalues, but plus one, minus one eigenvalues come in a lot and lot of places. So, this has nothing to do with variational algorithms. I mean, error correction is a completely separate field, and you can go and apply this error correction anywhere you want. It can be variational algorithm, it can be something else. Okay, coming to the last question, why are we considering chunks if S1 to S6 checks all the qubits? Well, the reason is that it's easier to think in terms of chunks. You can say that it is not a chunk, that is acceptable. But we know that for 3 qubits ZZI IZZ, we have explicitly seen how this works. ZZI IZZ. So if you think of these three as a chunk of qubit, 3 qubits forming one chunk, then essentially S7 becomes XXI. So it becomes very easy to understand that if ZZI works, why XXI should also work. That is why in terms of understanding, it is easier to think in terms of chunks and consider XXI. But strictly speaking, if you are asking this, you are right that these are not actually chunks, or we cannot apply directly some gate on chunks. We have to apply explicitly each of them. But here, this is actually correcting bit flip for the first 3 qubits, these two. It doesn't care about the other 6 qubits, but the other 6 are taken care of by the other stabilizers. So we already discussed the practical uh, example of an error syndrome and correction, right? Here we explicitly did one example where X is operating on the first qubit. What happens? We did all the calculations here, that what happens when we apply all the C0 gates, and then we do the syndromes and what this syndrome means and what the corresponding correction means. Uh, Here also we saw that if I have these two stabilizers and there is an error on the first qubit, they correspond to this -1 and +1 eigenvalues. This is in some sense the syndrome extraction here. Previously, we had the qubits, which can be zeros and ones. Here, I am talking more mathematically as eigenvalues, which can be +1 or -1. But again, as I said, just to reiterate myself, +1, -1 eigenvalues, they just go back, and they, when you, if you want to apply it on a circuit, you have to apply the way we saw first. There will be syndrome qubits. Essentially, you will have zeros and ones. But if you just want to explain it mathematically to anyone, it is way easier and simpler to give them the stabilizers. That's all. But these two are equivalent. Okay, coming to yesterday's session where max cut is applied. Yes, of course, max cut is not minimal. Like min cut is a problem that we can solve in polynomial time. If there is a problem we can already solve in polynomial time using a classical computer, there should be a very strong reason to go to a quantum computer to solve the same problem. Max cut is a NP hard problem and an APX hard problem. One example that I gave you was that if you think I am using this Vodafone, I use Vodafone, I am using this Vodafone um, connectivity and it is connecting to one of the towers. So you can think that the towers are, say, green nodes and the users are the yellow nodes. If one of the edge gets cut, then you want to, the connection, the mobile will take the connection from some other tower. But if, say, 5 towers get cut, then maybe that mobile loses connection completely. There is no nearby tower from where it can connect. But the max cut here is, uh, it's kind of trying to say that in terms of telecommunication, I want to ensure that if I have my users, which are maybe my yellow nodes, and if I have my towers, which are my green nodes, this can tell me how to place the towers, and depending on the density of users, how the users usually move, so that this number of cuts, number of connectivities from the user to tower that needs to be cut so that the user loses connectivity is very high. So as I said, it's possible that one tower fails, but 5 towers fail simultaneously. That is very rare, right? So this is one possible example where max cut can be applied. Okay, so that's a good question. What does the term stabilizer means? Stabilizer actually comes from this group theoretic idea. It is, I have even forgotten the exact definition. It is the normalizer of a group with some particular property. I have exactly forgotten the yeah, I have forgotten the exact definition here, but you can just search for a stabilizer of a group. It is a well defined thing, and these operators, the way these are created, they actually satisfy those requirements. It's a normalizer of a group requirement. Okay, if there are no more questions, maybe we can end.
Thank you so much, sir, for this informative session. And thanks to all the participants. Day after tomorrow, we will meet at same time, 3 p.m. Thank you so much, sir.
Okay, thank you. Bye.
Participants, there is no class tomorrow, no?